we are going to find a feedback gain k as we did in the previous lectures. The outcome of this will be a feedback gain k. Okay? There will be a feedback gain. So what's the difference? In the previous problems, I was always giving you a desired eigenvalue. I was telling you, let's move the eigenvalues to this point. Where was the desired eigenvalue coming from? I was giving it to you. Where is it going to come in real life from? Well, there's not going to be some magical person who will tell you the desired eigenvalue. It will probably, again, you who will decide on the desired eigenvalue. So how do you decide on the desired eigenvalues? Now here, we are not defining a desired eigenvalue. We are still finding a feedback gain k. The feedback gain k that we will find will move the eigenvalues to a certain point. Okay? How and where will it move it? It will move it to a point such that j is a minimum. Okay? So we as control designers are no more trying to move the eigenvalues to a desired point. We are doing something different now. We will be at the end choosing, I just removed it, the weight matrices F, G, and decide which one is more important. And the optimization problem will take care of the rest. The optimization problem will make sure that X is moving little, U is moving little, okay? And move the eigenvalues to a certain point. That is an outcome of this optimization. So we are still trying to find feedback gains k. Nothing has changed, except we are not giving a desired eigenvalue. The desired eigenvalue or the resulting closed loop eigenvalues will be the outcomes of this optimization problem. Is that clear now? Okay. So, still here, still trying to optimize, still try to find the minimization of j. This has just gone. One question was, well, how do we do this? Because at the beginning we didn't do it in this problem. Well, here we added into the problem. Here we are looking at the variation, and because we are looking at the variation, I can do this. The variation I say is small, and therefore I can set it equal to 0. So, I mean, from here on, it's a little bit mathematics. I mean, we will get some result and apply to our problem, but here it is just mathematics. So bear with me. It's not too long. We are almost done with this mathematics. So this is gone. We're going to look at this part now. This is the difficult one, and maybe look a little bit on this one, and then we will have some conditions and results. So let's look at this one. Look at the variation of this part and see what this looks like. So T0, TF. Any questions about what I just explained? And do you understand what we are trying to do here now? Okay. The T d del x dt times dt. And we will use integration by parts. Okay. This is integration by parts. Integration by parts. And you obtain okay. So I hope you remember integration by parts. So this is del x dt, right? Times dt, and taking the integral, you have dt over here. So what's going to happen is that you're going to have an integral from t0 to tf for this part, and then for that part. Okay? And this is how it looks like at the end. And this is something you hopefully remember from your calculus class. It's called integration by parts. So let me remove this. Okay, now add this thing to that part, and we have the following, delta J. T0, Lx, T0. So all I did was I added this part, basically this part, I added to this, okay? And when I do this, I get these two parts, of course. They are here, okay? And I still have this one. That is here. And the integral will have these two plus this, right? It has these two plus this. So it's just adding this part to that. And this is what we have. Which one? This one? It's this one here. Calculated at TF. This is calculated at TF, this is calculated at T0. So this one here is lambda TF delta X, right? That's the one you're talking about, right? So these two are calculated at TF, lambda TF, lambda TF. So if you add them over here, right, it's outside of the integral, so it will just move over here. And I put it into the delta X TF parenthesis. You see? So it's this one plus that one. Okay? So we're almost done. So it's not as difficult as it looks. It's, some mathematics. Okay. So, first observation here, variation in xt0. xt0 is the initial condition of x, which is known, and there's no variation in xt0. Right? Where does this xt0 come from? It comes from here. Del x at t0. Del x at t0. So, del x at t0, there's no variation at t0. We know the initial condition. We know where we start, okay? Therefore, there's no variation in the initial condition. So therefore, this is equal to 0. There's no variation in the initial condition. There is a variation there's a question of where we end up, the final. But the beginning, we know where we begin. So therefore, there's no variation in it. So this is equal to 0, okay? Good. So, now, let's select the following. Let's say lambda T F is equal to this. D, phi, dx of tf. Okay? Let's select it this way. I mean, this Lagrange multiplier is what we choose over there anyway. I mean, I'm trying to set this equal to 0, right? That's the goal. So if I choose the Lagrange multiplier like this, then this term will go, right? This term will just go if I select it like this. So this is now my first selection. So that's gone. This is gone. So all I need to take care of now is this part. And if I can set this equal to 0, then I have my solution. For this one, I can use this. The Lagrange multiplier minus del h del x. Right? That's del x del h. If I choose it like that, because this is free. Lagrange multiplier is free. It doesn't mean anything. So I can choose that. So if I choose this, then this is gone. And this is my selection number 2. And the final selection is here. If I choose del h del u to be equal to 0, this should happen. I mean, this is one condition here. Then this will become 0, and I'm done. Then I have everything equal to 0, and that is what I was looking for. Okay? 3 conditions. Of course, you might ask, why didn't you choose delta u to be equal to 0? Right? I could choose either one of them. I choose this one, del h del u is equal to 0. Why didn't I choose delta u equal to 0? If I choose delta u equal to 0, then this will be free for this term I'm talking about, right? Well, I can't choose delta u equal to 0 because u is the control. And the control can be quite large. U is free, and the variation in u can be large because it's the control. It's free. So I would rather choose del h del u to be equal to 0 rather than this one. Because we are looking at small perturbations. This delta here is for small perturbations, small perturbations, small perturbations, not large, but small perturbations. And therefore, you have small perturbation over here. And del u is not necessarily small. U is the control, it can be large. Therefore, I'm choosing this one. Del h del u equal to 0. So, 3 conditions. So, if I can solve this, then del j will be equal to 0, and I have a solution. Is that clear? Okay? Question is, can I solve it? Okay? We have these 3 conditions. Well, the answer is yes. We can solve them. And these are the 3 conditions that I need to solve in order to set this equal to 0 and therefore find the minimum point. Okay? This is what we call the transversality conditions. You don't have to remember this. I'm just writing this down so it's a reference for you. Transversality conditions. We call the transversality conditions. This here this is a differential equation. Equations. In fact, equations. How many of them? Well, there will be n differential equations. Right? There are n equations here. N differential equations. N differential equation. Why n? Because it depends on the number of x. Because this is a partial derivative, right? And you will have n of them. I mean, remember that x is can still be a vector there. So you have n differential equations here for this one. this one here are algebraic equation. Oh, no, this is a terminal constraints. Terminal constraints. In fact, n terminal constraints. You have m number of terminal constraints. And here you have algebraic equations. On top of this, we have another condition. Of course, we have the x dot equals f condition, right? Which is coming from our problem. Oh, let me write it here. X dot equals f, and this is condition number 4. And here we have another set of n equations, n differential equations. What else do we know? We know the initial conditions. We know x0, t0. Where should I write this? Let me write it down here. No, x t0, which is x0. And these are n initial states. N initial states. So this is everything we have in hand. Okay, this is everything we have in our hands. If you want to set this equal to 0, then this is all I have. What do I have? I have n terminal constraints. Basically, if you solve a differential equation, you either need to know the beginning or the end. You need to have the constraints. If you know the beginning the initial condition, and you have the differential equation, you can start from the beginning and calculate the differential equation. Or you can do vice versa. You know the end point and you know the differential equation, then you go backwards and you can still calculate the function, right? You need one of the terminal constraints. So I have n differential equations here, n differential equations here. So basically I have 2n differential equations. Trying to see what to remove here, maybe this part. What do I have now? I have 2n differential equations. I have n boundary conditions for the beginning, for the initial condition, but I also have n boundary conditions at the end. So I have 2n number of boundary conditions. Can I solve this now? 2n number of differential equations, 2n of boundary conditions. So this I can solve. Right? On top of that, to do the optimization, I have del h del u equal to 0, and that's my algebraic equation that I need to solve in order to find u. And that's my solution. That's my optimization problem. 2n differential equations, 2n boundary conditions. I can solve that, and I have to find u from this algebraic equation del H del U equal to 0. If I do that, then this will become equal to 0, and that will hopefully be my optimum U that I will find from this. You understand that? You don't have to understand every single detail right now, but you have to understand what I'm trying to do. We had the optimization problem. I hope you understand that. The optimization problem, I'm looking for weak variations. Okay? Delta J. I did mathematics. This is just mathematics. You can go through that at home. Okay? And I'm trying to set del J equal to 0. Because when del J is equal to 0, that means I found a minimum or a maximum. In this case, hopefully it's a minimum. Okay? So I'm trying to set it equal to 0. So this is my equation. How do I set this equal to 0? These are the conditions. If this is equal to that, that term is gone. This term is gone anyway. If this is equal to that, this will be gone. If del H del U is equal to 0, that term is gone. So this is equal to 0. So I'm just writing this down. This. 3 conditions. This will set it to 0. Now I'm looking at what I have in hand, and I am trying to understand if I can solve this. Because I have a differential equation here because of this. I have a terminal constraint. I have this. Can I solve this? Is there a solution to this? So I'm writing everything that I have in my hand. I have these 3 from this. I have this one that comes from the problem. And I have this, which is the initial condition. Question is, can I solve all this? Answer is yes. I have 2n number of differential equations according to this. I have 2n number of boundary conditions. So this should be solvable. And I have an algebraic equation from which I can find U. So this was the goal, and the problem is complete. Mathematically, I can solve this. And when I find U, this will be the U that will minimize J. Okay? Now you will see that U will depend on X, and you will be able to find a feedback gain K from this U. It's amazing mathematics, right? And the solution is also quite amazing. So you might, of course, say, who came up with this? Who found all this? Well, it's humanity that was working for hundreds of years on these problems. Okay, it doesn't come someone sitting, having a coffee and writing all this down in one night. Okay, it's a lot more than that. It's a lot of mathematics, it's a lot of understanding, it's control theory, concepts, and all this. All right? Understood so far? All right, so let me give you an example. Before I apply this to our problem, I want to give you an example, an optimization problem example, so you see how we are going to apply this concept to an actual problem. Can I remove this? I mean, you understand this, right? Okay. All right. So let's do an optimization example. I mean, this is not a controls problem. It's just an example of optimization. Let's say J, the performance index, or the cost function, et, subject to x that equals u. X 0 is equal to 1. Find U that minimizes J such that I just rewrote the problem in words. I mean, this is not, you know. The problem is find u that minimizes the function j such that x dot is equal to u with initial condition x0 is equal to 1. Okay. So do you understand the problem? I mean, don't look at this as if it was some strange hocus pocus. Okay? There's a function called j. All right? The j function is an integral from 0 to 1, and it is u minus x squared times dt. All right? So, however, x and u, they are connected. They are not independent from each other. In fact, the connection is x dot is equal to u. So, as time goes by, time goes from 0 to 1, x moves in a certain way. How does it move? Well, if you move u, then x dot will move, and therefore x will move. And therefore, this u and x move together as time goes from 0 to 1. Now the question is, let's start x from 1, find the u that will minimize j. Sounds like quite a complex problem actually, right? Because x and u, they are connected through a differential equation. But fortunately, we have a solution now. We know how to do it. Actually, it's here. Okay? So let's apply these conditions to that. First of all, this is here now L, right? The way we found that. This one here is now F, right? We had that. This is F. That's F. That's L. And phi is equal to 0 for this problem. Phi is equal to 0. So it's a little simpler. Okay? It's a little simpler. And H, the Hamiltonian, was equal to L plus lambda F, right? It's here. That's the Hamiltonian. So L is here, u minus x squared plus lambda is lambda, F is u. Okay, that's H, Hamiltonian. So I can immediately write the first thing, del H, del u. So that's my first condition, del H, del u is equal to 2u minus x plus lambda, and that should be equal to 0. So that's condition number 1. So in other words, u is equal to x minus lambda 2. Yes? Yes, but this is a one-dimensional problem, therefore I don't write the transpose. It is one-dimensional, right? It's a very simple problem. If x was a matrix or a vector, then it should be like that. Yeah. I mean, see, this is solvable, but the solution is not always easy. Okay? Usually you need a numeric solution, and this is not very easy to solve. But because we are in class, we want to do something quick, I make it a one-dimensional problem that's easy to solve. Okay? Of course, you cannot always solve it by hand. All right? So this is first condition. So we used number 3. Okay? We used number 3 that we want to use. So let's use the other ones. Let's use the second one. Right? Lambda dot. Let's call this 1. Let's call this 2. The second condition is lambda dot is equal to minus del h del x. And that's also pretty straightforward. I know h. So that's equal to 2u minus x. Okay. Let's use the third condition. Final time is 1, so lambda 1, okay, is equal to d phi dx1 and phi is equal to 0, therefore this is equal to 0. Okay? So another condition I found is lambda 1 is equal to 0. This is that. And here I found lambda dot is equal to 2u minus x. That's the other one. Okay, and I have, what else do I have? I have x0 is equal to 1, right? x0, that is already given in the problem. And I have x dot is equal to u. Good. Look at this. Two differential equations, two terminal constraints. I should be able to solve this, like here. And then I have that. And u is equal to that. Two terminal conditions, two differential equations. I should be able to solve it in one condition for the optimization. Okay? It's a one-dimensional problem, therefore I have two differential equations. N is equal to 1, one-dimensional problem, two differential equations, two boundary conditions. And from now on, it's just simple mathematics or algebra, whatever you want. Okay? So I'm just going to solve this now. I mean, this is just, as I said, just some calculations from here on. But I know even if I cannot solve it by hand, I can probably solve it numerically. But in this case, we will be able to solve it here on the board real quick because it's a really simple problem. So here from now on, it's just mathematics. Lambda dot is equal to 2 times x minus by 2. So I'm replacing this u with this minus x. So that will go. Lambda dot is equal to minus lambda. And from here, we obtain lambda. I know the solution to this, of course. It's c1 to e to the minus lambda t. And since I know the terminal condition, I can solve this. So C1 is equal to 0. Therefore, lambda t is equal to 0. So that's 1. So as a result, u is equal to x minus lambda divided by 2. And since this is equal to 0, so that's equal to 0. So u is equal to x. Plug into x dot is equal to u. You get x dot is equal to x. And from that you get, again, the same thing. And I know x0 is equal to 1. So xt is equal to e to the power t. Okay. Oh, no. Wait. 1 is equal to c2 times e to the power 0. c2 is equal to 1. So x of t will be equal to e to the power t. So that's that. Because of this and this, you get u is equal to e to the power t. And that is your result. And this is what we call the necessary condition for minimum j. Necessary condition for minimum j. Or to minimize, for a minima, let's going to minimize j. ij. Why do I call it the necessary condition? Because we are only looking, we have been only looking at the first variation. So we looked at the first variation and then we set it equal to 0. We look for weak variations of j. So we know it's a minimum. Okay? I don't know if it's the global minimum. I'm sorry, I don't know if it's a minimum. It could be a minimum or a maximum. We don't know that, right? And we don't know if it's, even if it's a minimum, we don't know if it's a global minimum. We don't know that. But we know this is a necessary condition. I mean, if it's a global minimum, then the first variation must be equal to 0. Okay? Therefore, we call it a necessary condition. It is not sufficient condition. For a sufficient condition, you need to look at the second variation. For this, we only look at the first one. Okay? Now, turns out the linear LQR problem will give you the solution even for the necessary condition. But for this little problem here, we only have a necessary condition to minimize j. Hopefully, this is a minimum. Hopefully, this is a global minimum. But we don't know, of course. Okay? We only look at the first variation and set it equal to 0. And this is your solution for that. I call it the necessary condition to minimize j. Okay? Now you see, this was a problem. I said find u to minimize j. And that's your u. If you apply this u to the problem, then j will be minimum, hopefully. At least I know it's a necessary condition to minimize j. Okay? Did I have a terminal constraint? Did I wanted anything at the end, at the end for t final? Nothing. There was no constraint on the final. So I can safely say that x1 was free. It can be anything it wants. But if you want, you can try at home, add a condition over here, and then try to minimize that. But I warn you, it will not be very easy. You might need to solve this numerically. I mean, here I have a nice function, but you don't always get this algebraic nice function. You understand the idea? Okay. Now, what we're going to do next Monday is we are going to take this concept and apply it to our controls problem. And we will be able to find a feedback gain k that will be optimal in the way I explained in the first hour. Okay? And that will be the LQR gain or the LQR solution for this problem. All right? So this Wednesday or next Wednesday, I will email you. I will have a class. I will do more of a recitation type class. I will do MATLAB Simulink. I will show you different controllers. I will, not this one. I will talk about the integral controller. I will talk about the previous feedback gains and how I apply this to airplanes and things like this. Okay? So it will be a class in MATLAB, Simulink, recitations, and all that stuff. So you will not lose material if you don't come to class, but it will be just a nice recitation. Okay? And it will be a relaxing class. So even if you have an example, a midterm later, you will not be too tired. Is that good? Okay. So I will email you. Okay? So see you